Yes, today we are going to learn about integration of radar pulses. Here, the integration of radar pulses nothing but actually if a radar propagate electromagnetic waves towards the target, along with the target, some unwanted targets also okay present surrounded by original target. Due to that unwanted targets and as well as original target, the radar receiver receives all the echo signals. Okay, due to the target and as well as due to surrounding objects, the radar receive all the echo signals. This will be integrated, okay, with different time slots. Okay, on the screen, on the indicator, the observer can observe all the integrated of radar pulses. It can be given as n suffix b is equals to theta b by theta s into f suffix b. Here theta b is the antenna beam width in terms of degrees. Okay, units is degrees. Here theta s is the scanning rate, antenna scanning rate. Units for this is degrees per second. We can write theta s in terms of omega m, that is antenna scanning rate, that is rotations per minute, units is rotation per minute, and sigma. Okay, theta s is equals to sigma into omega m. Sigma is nothing but radar cross section, that is cross sectional area of target. Okay, we can write theta s is equals to sigma into omega m. Then incident energy can be given as E suffix I of n, that is incident energy, that is transmitted energy. Okay, can be given as for n number of pulses, that is n number of echoes, okay, received by the receiver and integrated on that screen, okay, in the receiver session. It can be given as signal to noise ratio for a single pulse, okay, to number of echoes, okay, that is n number of echoes, signal to noise ratio for n number of pulses. This is the ratio between single pulse to n number of pulses. Okay, this is the integration of radar pulse. We will see by using onboard software. Here n suffix b is the number of pulses, that is number of echoes received by receiver antenna, theta b divided by theta s into f suffix, that is f suffix p is the pulse repetition frequency. F suffix p is the pulse repetition frequency. Theta b is the antenna beam width. For example, if you are taking a horn antenna, like this, horn antenna transmitted some electromagnetic energy then this is the beam. We can take the beam width. Okay, this is the beam width, theta, in terms of degrees. Okay, and theta s where theta s is if your target is located at east direction. For example, if your target is present at east direction, we have to use one antenna, and if the target is present at west direction, we have to place one another antenna at west direction to track the target. If you have north and south, like this we have four directions. So for that, if we use four antennas, what happens? The cost of the system, radar system, is also increases. To avoid that, we can replace single antenna. Okay, instead of using four or five antennas in the horizontal direction to cover all the direction, we can use a single antenna. But we have to rotate this antenna in a horizontal direction, okay, to track the target. That is, we have to rotate this antenna in a horizontal direction, whether in a clockwise or anti-clockwise direction, to track the target, okay, in all the directions. For example, if the target is present in east direction, it will track it. Okay, if the target is present in north direction, then the antenna is rotated in this direction. So for that, the antenna definitely track that target. So this is theta suffix s. Theta suffix s is the scanning ratio. Here the antenna is scanning in all the directions: east direction, north, west, south, east, like this, from 0 to 360 degrees it is scanning. Okay, it is scanning the targets, whether it is present in east, west, okay, like that. Okay, and it directly shows on the indicator PPI scope. Okay, PPI scope is a plan position indicator scope. It is a three-dimensional. Okay, on the screen we can observe whether the target is present in which direction. Okay, like that, the antenna have to rotate in all the direction in order to track, okay, in order to scan the targets. It is the thing. This type of rotation in a horizontal direction, that is azimuth angle. Okay, we can measure in terms of azimuth angle. We can call it as azimuth angle when antenna is rotated in a vertical direction. For example, a aircraft is moving 10 kilometers at height, okay, above from the ground. If you are rotating antenna in a horizontal direction only, there is no use. Okay, why? It means because aircraft is moving in a upward direction, right, about 10 kilometers height. What we have to do? We have to rotate antenna in vertical direction also. Okay, along with the horizontal direction, the antenna also move and rotate in vertical direction also. Okay, that means antenna have to rotate in vertical direction and as well as horizontal direction. The movement of antenna in a horizontal direction is called azimuth angle. The movement of antenna in a vertical direction, it is called elevation angle. Okay, both are, we can, in terms of units, is nothing but degrees only. Okay, when the antenna is moving in all directions, azimuth and as well as the elevation, then it can cover all directions. Okay, then it will scan in all the directions, east, west, north, south, along with top of above from the ground, and like this it can a imaginary globe. You can imagine a imaginary globe. Okay, in all directions the antenna will cover and it will scan whether the targets are present or nothing. Okay, like this it scan. Okay, if the number of targets, okay, if your target is present in east and if your target is present at north also, okay, unwanted target. Okay, so due to in the east direction target and as well as in north direction target, we will receive that two echo signals. It will be integrated in the receiver session. So depending upon scanning ratio also, scanning okay, theta s is the scanning rate. Okay, it is also depending upon that. Okay, theta b by theta s. Theta b is the antenna beam width. Okay, first of all it radiates electromagnetic waves, no, like this. Okay, if you take a torchlight as an example, why it means because electromagnetic waves properties and light properties is very similar. Okay, so light is visible. Okay, so for that I am taking as example for horn antenna. If you instead it is a horn antenna, right? Okay. For example, if you take a torch, okay, the light, okay, is also deviated. Okay, it has some beam width. Here also the same thing. The radio electromagnetic waves, okay, with the help of horn antenna we are propagating electromagnetic waves. It will looks like some beam. Okay, okay, the beam width, it is the beam width, and the beam width divided by theta s. Theta s is the rotation, okay, scanning rate. Next, instead of writing theta s, we can write theta s is equal to sigma into omega m. Sigma m is the radar cross section. Okay, here we already see, right? Sigma is the radar cross section, that is the cross sectional area of a target. Okay, omega m is the antenna scanning rate, it is rotation per minute. Okay, theta s is the antenna scanning rate, it is also the same thing, the units is degrees per second. Here omega m is the antenna scanning rate in terms of rpm, rotation per minute. Okay, this is the thing. So theta s we can also write in terms of theta s. Theta s is equals to rotations per minute, okay, scanning rate, and as well as sigma. Sigma is the cross sectional area of targets. F suffix p means it is a frequency, okay, pulse repetitive frequency. We have to include this, okay, in order to calculate integration of pulses. How many pulses are integrated at the receiver section means depending upon theta b, theta s, and as well as f suffix p. Okay, this is the thing, ma. Okay, you have to maintain notes for this. I have already posted that. And when you go for incident, okay, energy, okay, for n number of pulses, E suffix I of n is equals to signal to noise ratio for one pulse to n number of pulses.